All right, so as x approaches 2 from the right, the function gets closer and closer to 5. It does never actually equal 5. Right? Never, ever does this function ever equal 5. That's okay. That's not what a limit's about.
Sorry, on the x side, that small number is 2, right?
Yeah, that is a 2.
Oh,
Yes, sorry, I know.
which function did you put it into? Is it the x squared plus 1?
That's an excellent question. Which function did I put it into? Well, I looked at the fact that x was larger than 2, since we're approaching 2 from the right. And in this piecewise function, the piece when x is larger than 2 is exactly x squared plus 1. So I could have shown a little more work here if I really wanted to. I could have written this as the limit as x approaches 2 from the right of f of x. Well, since x is larger than 2, we get to use the piece where x is larger than 2, which is x squared plus 1. And then, and we're going to see this a lot, for most limits, if we can just substitute in the value x is approaching and get a real answer, that's what we do. So we're just going to substitute in 2 for x and get 2 squared plus 1, which is 5. I should point out, a lot of people, when I show them this, they really want to say, James, shouldn't we let x like be 3 or something? No, x is getting super close to 2. You could say, James, I'm going to let x be like 2.1. I say you should go closer, 2.01, closer, 2.001, really super close, 2.0000000000001. And if you plug that in and you square it, it's going to be 4 point twice as many zeros, 1. Plus 1 is going to be 5 point a bajillion zeros, 1. It's going to be 5, right? Because the question is, the question isn't what value are we equal to, it's what value are we getting really, really close to. And the value we're actually getting close to is 5. We don't ever get there. But that's not the question. The question is, what value are we getting close to? I know I'm spending a lot of time talking about this, but it's because it's a really important idea, right? The whole, I mean, this is the basis for a lot of what calculus is all about. The whole gist here is that this function gets close to 5 as x gets close to 2 from the right-hand side. But it doesn't actually ever equal 5. That's okay. And then we can also ask, what's the limit as x approaches 2 from the left-hand side of the same function? So now, and this is where we need to be extra careful. If we're on the left side of 2, are we on the piece where x is less than 0? Or are we on the middle piece where x is between 0 and 2? Well, here's what we have to remember. X is approaching 2 from the left. So we're on the left side of 2, but we are getting close to 2, meaning we should definitely be picking this part right here, which graphically also makes sense. If x is getting closer and closer and closer to 2 from the left, the corresponding y values are getting closer and closer to whatever this piece of the function is getting close to, which happens to be 3. And again, you could show more work, right? You could totally be like, oh, sure. There it is. You could totally be like, I know that I am using, since x is just a little bit less than 2, we're in this zone here, and in that zone, the function is x plus 1. And then you can actually just plug in 2 for x. And I really have to say this very strongly, right? The reason we're allowed to plug in 2 is because x is getting close to 2. How close? As close as you want. Infinitesimally close. There's 0 distance between x, well, not 0, but there's a minute amount of distance between x and the number 2. So if x gets really, really close to 2, well, it makes sense that x plus 1 would be getting really, really close to 2 plus 1, which is 3. I will also point out here, the function actually is equal to 3 when x is equal to 2. Right? It's also true, oh yeah, by the way, f of 2 actually is 3. That has no bearing. There's no influence. Influence, I can spell, sure, on the limit as x approaches 2 of f of x. So it really, really, really does not matter what the function is equal to at the point that x is approaching. That's maybe an over-exaggeration slightly. It matters when we start talking about continuity, but as far as limits are concerned, the value of the function at the point is inconsequential. So I should point out that for this example, we would say the limit as x approaches 2 overall of the function does not exist. For the limit to exist as x approaches 2, the function has to be getting close to one particular value as we get close to 2 from either side. And the problem here is that from one side, we're getting closer and closer to 5. From the other side, we're getting closer and closer to 3. And they're not matching up. So if the left-hand limit and the right-hand limit aren't the same, the limit doesn't exist. Because the limit as x approaches 2 from the left of the function does not equal the limit as x approaches 2 from the right. Question so far? On the other piece of this function, where I should say where the other two pieces meet, if we ask, say, what's the limit as x approaches 0 from the left of this function? Well, again, graphically, we can see that as x approaches 0, the corresponding y values approach +1. Limit as x approaches 0 from the left of, well, when x is less than 0, the piece we're using, which I know you can't see anymore, the piece we're using is x cubed plus 1. And that's going to be 0 cubed plus 1, which is 1. And as x approaches 0 from the right, well, we can even see from the graph, right? As x approaches 0 from the right, the y values are definitely getting closer and closer to 1. So it is also true that approach 0 from the right, we're going to use the middle piece because that's the piece we're on when x is slightly bigger than 0. But when we plug in 0, we get 0 plus 1, which is 1. So for this particular piece of the graph, since the left-hand limit and the right-hand limit are the same, we can say, oh, the overall two-sided limit as x approaches 0 of the function is equal to 1 because the left-hand limit and the right-hand limit match up. Sorry. If you ever can't see something, just let me know. So again, limits are concerned with what the function values, the y values, are getting closer to as the x values approach some particular number. Let's look at another example. Let's say we have this piecewise function. F of x is x plus 2. When x is strictly less than 1. It's 7 when x is equal to 1. And it's 4 minus x squared when x is greater than 1. Let's graph it. So let's see. X plus 2 has a y-intercept of 2. And if x could be 1, y would be 1 plus 2, which is 3. But it can't be 1, so we have an open circle there, and it does this kind of deal. So there's y equals x plus 2 when x is less than 1. And then 7, 7 is a little too, I should have picked a smaller number. Pretend that's 7 there. When x is equal to 1, the function is equal to 7. And then when x is greater than 1, the function is 4 minus x squared. So 4 minus x squared looks like this parabola. Starting at 1, it goes like this. And just graphically, we can already see that the limit as x approaches 1 from the left and the limit as x approaches 1 from the right are both the same. And we can see that whether we come at 1 from this direction, the y value is getting closer to 3, or if we come at 1 from this direction, the y value is getting closer to 3. We can also write it out. Limit as x approaches 1 from the left of f of x is the limit as x approaches 1 from the left of x plus 2. And again, we're not plugging in 0. We're not plugging in 0.5. We are plugging in 1 because x is getting super extra close to 1. It's just a tiny bit less than 1. And the same from the right. When I look at the limit as x approaches 1 from the right of f of x, it equals the limit as x approaches 1 from the right of 4 minus x squared, because that's what the function is equal to on the right of 1. And then we plug in the 1, and we get 4 minus 1 squared, which is also 3. So this tells us the limit as x approaches 1 from either side of f of x is equal to 3. And I want to again stress, it doesn't matter that the function is equal to 7 when x is equal to 1, right? It is also true, oh yeah, f of 1 equals 7. That doesn't have any effect on the limit. So the limit value, the limit doesn't care what's going on actually at the point. When we talk about limits, we talk about what's happening is x gets really, really close, but not equal to 1 in this case. Okay, so I will also mention, just because it's going to come up soon, although this limit exists, you can also probably see that this function is not continuous. If you were going to graph that function, you'd have to lift your pencil off the paper to get that point up there. And that's a way we can see if something is discontinuous. From a limit point of view, the reason it's discontinuous is because the limit value and the function value don't match. If f of 1 were equal to 3, this function would definitely be continuous at that point. But it's not. I know we're getting a little ahead of ourselves there, but I just thought it seemed like a good example to mention it for. So we'll definitely revisit continuity next week, probably. So evaluating limits. The nice thing about evaluating limits is it's usually pretty easy. Usually, well, that's a giant lie. It's not really usually pretty easy. It's pretty easy if you can see the thing. It's also pretty easy if you can if you get something that exists. Meaning, the first thing you should do when you're trying to evaluate a limit is just say, what happens if I plug in 2 for x? In this case, I get 2 squared plus 3 times 2 plus 4, which is 14. Is it 14? Yeah, it's 14. Someone who wrote these notes here doesn't know how to add up. Or okay, let's fix that. Yeah. So, right, 4 plus 6 plus 4, yeah, 14. This limit's 14. And you can graph it if you want to, but the whole idea there is that we're just saying as the x values get closer and closer to 2, x squared plus 3x plus 4 gets closer and closer and closer to 2 squared plus 3 times 2 plus 4. There's no weird discontinuity or undefinedness at 2, so we don't have to worry about that. And this kind of works for a lot of things. If I want to find the limit, let's say x approaches 1 of the cube root of x plus 7 plus e to the x minus 1 plus 3, as long as I'm not going to get some division by 0 or the natural log of 0 or a square root of a negative number, I'm pretty good to get. The exception being piecewise functions. I'll just point out this function here, you could not find its limit as x approaches 2 by just plugging in 2 to the function. If you plug in 2 to the function here, you get 3. And we already showed that the limit as x approaches 2 doesn't exist because the left and the right-hand side don't match up. Most normal functions that aren't piecewise functions, usually their left and right-hand side are kind of doing the same thing. So we don't have to worry so much about that. But piecewise functions are often used as an example of discontinuous functions. It's kind of hard to make them up otherwise. So that's kind of what's going on there. Here, we're just going to substitute in 1. What we're doing here is what's called using the direct substitution property, which is that most functions, you can just plug in what x is approaching to see what the limit is. So we're going to get the cube root of 8 plus e to the 0 plus 3, which is 2 plus 1 plus 3, which is 6. So this particular function is getting closer and closer and closer to 6 as x is closer and closer and closer to 1. Now, things start to get more challenging when the function actually isn't defined at the point. For example, the limit as x approaches 3 of x squared plus 4x minus 21 over x minus 3. This is kind of your classic example of what I call a 0 over 0 type of limit. So if we plugged in 3, so you should always think about what happens when I plug in what x is approaching. So if you get a real number, 9 times out of 10, that's the answer. But sometimes, a lot of the time, when you plug in what x is approaching, you're going to get something not that great. If we plug in 3 here, I'm going to get 9 plus 12 minus 21. Oh, that's 0 over 3 minus 3. Oh, that's also 0. And unfortunately, 0 divided by 0 is not 1. Well, I mean, actually, it could be 1, but it could be 5 or 17 or a billion or negative 26, right? Because how many times is 0? Have we talked about this before? This is where I'm like, I know I've said this before, but it's probably my 20-minute class. How many times does 0 go into 0? As many as you want. Pick any number. I'm going to pick 7. It works. 7 times 0 is 0. 0 minus 0 is 0. Oh, there's no remainder. I win or I lose, right? Because really, that's not the answer. Because we could have picked literally any real number and we would have gotten the same result. So what we're seeing here is that 0 over 0 is what's called an indeterminate form. What you should really see when you see those words is we have to do more work. Because the answer could be anything, so we need to figure out what it actually is. Because there is a specific value, this limit, this 0 over 0 thing is getting closer and closer to. I know I didn't write that very nicely. It says indeterminate, I-N-D-E-T-E-R-M-I-N-A-T-E form. So here's what we typically do. Well, actually, before we do this, let's actually plug in some numbers. It's easier to see if you, yeah, so it's really easy to see if you plug in, like, let's say x was equal to, I don't know, 0.01. So if I did that, oh, question. Oh, no, okay. So if I plugged in x equal to 0.01, let's see what I get. I'm gonna make the math. Why would I plug in 0.01? That's not what x is getting closer to. What's it close? What's the number that I should actually pick? Or 3.01. Actually, I'm really trying to be close to 3. So I plug in 3.01. What am I going to get? Well, I'm just going to do the math because I don't really want to do the math. I'm going to get 0.01 on the bottom. And if you plug in 3.01 to the top, you're going to get, he says before he does it, you're going to get 0.04. Believe it or not. Let's check. That seems let's actually do the math. So 3.01 squared, that's going to be 9.0601 plus 3.01 times 4 is 12.04 minus 21 over, this seems like a really good idea, James. So let's see if we do this. It seems like it's not going to come out right. Probably because I didn't actually check my work. Let's check the work. 3.01 squared. It is. That's not right. That's the downside of using this phone. Oh, come on, stop being crazy. I'm not a fan of there we go. The phone, I keep like, okay, let's try this one more time. Sorry, I know this is just getting ridiculous here, but now we have to know the answer. Oh, no, I was right. It's 9.0601. And then this times 4 is 12.04. Okay, we're good to go. So that's ends up being 21.1, I think, right? Sorry, 21.10001 divided by 3.01. It seems really close to this is not the smart way to do it. You think I made a mistake? Oh, I definitely made a mistake. Yeah. And it's minus a 21, maybe. That's a little better. This is what happens when you try and do things and you didn't like actually plan on doing it. So reading 0.1001 divided by 0.01, which is looking like 10. Oh yeah, 10. 10.01. Is that what I wanted? I don't know. I don't know what the limit is. Let's find out. So here's what we're really doing. So if we actually look at this expression, well, we can simplify it. And if we factor the top, how's the top factor? Well, here's a nice thing to know. If we plugged in 3 and got 0, x minus 3 should be a factor. What's the other factor? Well, I need x times x to give me x squared. I need negative 3 times positive 7 to give me negative 21. That works. So here's the great thing about this. As x is closer and closer to 3, well, now I can see that the work I did before is actually right. If we plug in x equal to 3.01, these parts would cancel, and x minus 3 times x plus 7 over x minus 3, if x is 3.01, is going to give me 3.01 plus 7, which is 10.01. Let me show you what I'm saying here. So what I want to point out is that these expressions, x squared plus 4x minus 21 over x minus 3, and x minus 3 times x plus 7 over x minus 3, these are the, well, these are definitely the same, but these are also the same. Well, I should say, sorry. I should say, these are the same everywhere except for where? What value of x are these not the same at? Right, if I plug in 3 here, what do I get? 3 plus 7 is 10. Okay, so check this out. If x is equal to, let's start a little bigger. If x is 3.1, I could try doing the dumb thing I did before and plugging it in here and actually doing all the math. But what I really should have done was factored it first. So when I plug in 3.1 here, 3.1 minus 3 over 3.1 minus 3, those cancel. And we're left with 3.1 plus 7, which is 10.1. And if we plug in 3.01, we're going to get 3.01 plus 7, which is 10.01. And we can see that as x gets closer and closer and closer to 3, the y values are getting closer and closer to 3 plus 7. So as the x values approach 3, the y values get super duper close to 10. Now, in practice, this is not what you want to do. In practice, you want to say, well, look, this limit is equal to this limit. How am I allowed to say that? I mean, I know we just canceled the things, right? Like, yeah, you just cancel them. But really, why do I get to say that the limit of this and the limit of this are the same? Well, because these functions, x plus 7 and x minus 3 times x plus 7 over x minus 3, they're the same everywhere except at 3. And the limit doesn't care what's happening at 3. The limit cares what's happening very, 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 very close to 3. But actually at 3, all bets are off. We don't actually care. So as far as this thing is concerned, it's the same as this thing everywhere that matters. And then it's very not terrible to see that the limit of this is just 10. graphically, here's what this looks like. This expression, y equal to x minus 3 times x plus 7 over x minus 3, exactly looks like the function y equals x plus 7, except it's undefined at 3. So it looks like this. Let's try and make this look not terrible, sure. That looks a little terrible, sorry. Could have been better. So here's the y-intercept at 7. Right? If x is 0, y is 7. And here is the y value of 10 and the x value of 3. And as far as this function is concerned, as x gets closer and closer to 3 from either side, the y values get closer and closer and closer to 10. We don't care that they're not actually ever equal to 10. So that's kind of a lot of words to say. When you're trying to evaluate a limit, one of the things we typically do is we try and factor and cancel out the factors that are making it 0 over 0. If you've got a 0 over 0 thing, your goal is usually to cancel out the thing that's making it 0 over 0. All right, so let's look at some other examples here. Oh. Got all this paper that's got stuff on one side. Use the other side. All right, so let's look at this. What time have we got? This class is never enough time. So here's a lovely looking limit. And we can see readily that if we plug in x equal to 1, we're going to get 4 plus 5 minus 9 on top, which is 0. And 6 plus 7 minus 13 on the bottom, which is also 0. So this is definitely a 0 over 0 type of limit. So here's what I know already. I know that plugging in 1 got me 0 on the top and the bottom. So I know that what has to be a factor. Something like x minus what? 1. We have to have x minus 1 as a factor if x equal to 1 is making it 0. I think it's like the fundamental theorem of algebra or something that says that that's true. But that makes it easy to factor these quadratics, right? If you know that x minus 1 is a factor of 4x squared plus 5x minus 9, then you can very, very easily jump to the conclusion that the other factor has to have a 4x, so that the beginning part multiplies out right, and a plus 9, so that the end part multiplies out right. And you don't even really need to check the middle. You can. We check it, we get a negative 4x plus a 9x, which is a 5x. Great, it works. Same idea down here. I know it has to be a 6x plus a 13, so that things multiply out correctly. And then we can cancel those terms. We get the limit as x approaches 1 of 4x plus 9 over 6x plus 13. When you're finding a limit, do make sure you write the limit in every step until you actually substitute in x equal to whatever x is approaching. If you just wrote that, you would mean something completely different. This is a function. It does stuff. But this is a limit saying, I want to know what this function is doing as x is getting closer to 1. If you don't write that part down there, you've lost that meaning. So definitely make sure you write that. It's final. And then when you plug in 1, then you no longer need to write the limit because you were finding what the value we're approaching is. 4 times 1 plus 9 over 6 times 1 plus 13. We get 13 over 19. Right. There were, let's see. There's just so many things to say about limits. So let's go. I kind of wanted to come back to this, but I think there were a couple of questions I want to address. So we'll move around a little bit. Let's fine. I'm going to do 2 quick examples, and then I'm going to show you guys the squeeze theorem. Yeah, question.
So, like, I just said that 13 over 19 is the answer?
Correct.
Oh.
So if someone asks you, what's the limit as x approaches 1 of 4x squared plus 5x minus 9 over 6x squared plus 7x minus 15, the answer is that the limit is 13 over 19. And you definitely should show this work, but yeah, that's the limit. And again, what that means is as x gets close to 1, this function gets close to 13/19.
So like on a test, is there a certain way that I need to write it? Do I need to?
If I was to, if this question was on a test, I would write the answer exactly this way.
Oh, okay, just show the work and then
Right.
circle that. And be like,
Yep.
okay.
Yeah. What if we have the limit as x approaches 2 of the square root of x? Let's do this. The 3 minus the square root of x plus 7 over x minus 2. And again, you might note it's a 0 over 0 type of limit. No surprise. Oh, also, by the way, before you leave, make sure you fill out the attendance form by scanning one of the laminated QR codes on the chalkboard. You don't have to do it right this minute, but when you have a second. This is 0 over 0 type, right? 3 minus 3 over 2 minus 2, definitely 0 over 0. And the way we deal with a 0 over 0 here, well, I can't really factor anything. When you have a square root plus or minus something else or something plus or minus a square root, the usual tactic, whoops, don't write the limit again. The usual tactic for dealing with this sort of limit is to multiply it by the conjugate. 3 plus the square root of x plus 7 over 3 plus the square root of x plus 7. I should specifically say you're multiplying by 1, but the 1 is the conjugate of the square root part divided by the same thing. And the reason we do that is because then things get nicer. So when you multiply this out, 3 times 3 is 9, and the middle terms cancel. That's the whole point of multiplying by the conjugate. I don't really want to write them out. I'm just going to point out that if you FOIL this, you get 3 times 3, you get 3 times root x plus 7, and you get 3 times negative root x plus 7, and those cancel. And then you also get negative root x plus 7 times root x plus 7, which is going to be negative the square root of x plus 7 squared. Over, do not multiply with the bottom part. Because we are trying, or generally the part that's not the conjugate. We're trying to cancel the thing that's making the top and bottom 0. And the fact that it's making both of those 0 is an x minus 2. Because you plug in 2, 2 minus 2 is 0. And I'm not really seeing that on top here. So I need to do some work. And the limit as x approaches 2. Square root of x plus 7 squared is x plus 7. So here's where it's easy to make an error. Oops, well, it's really an error if you write 6 instead of 7. So I've made a small error there. Because all of a sudden, the top went from being 0 when I plugged in 2 to not being 0 when I plugged in 2. Right? 9 minus the square root of 9 squared is 9 minus 9, which is 0. Whereas 9 minus 2 plus 7 is 7 plus 7, which is 14. What did I forget? Right. So it's really 9 minus all of that, which is x plus 7. And then if we simplify a bit, 9 minus x plus 7 is 9 minus x minus 7, which is 2 minus x. X minus 2 times the square root, times 3 plus the square root of x plus 7. There's a couple ways of dealing with a 2 minus x divided by an x minus 2. One way is to say, whenever you subtract things in the opposite order, they're negatives of each other. 5 minus 8 and 8 minus 5 are negatives. One's 3, one's negative 3. And when you divide them, you get negative 1. Or you can factor out a negative. You could totally write this as the limit as x approaches 2 of negative 1 times negative 2 plus x, or x minus 2 over x minus 2 times 3 plus the square root of x plus 7. That's also perfectly fine. So the x minus 2 and the x minus 2 cancel like we wanted them to. And then we can plug in 2 for the remaining x's. Negative 1 divided by 3 plus the square root of 2 plus 7. which is -1 over 3 plus 3, which is -1/6. Okay. So, yeah. There's one other type of, well, not just one. There's one more specific type of 0 over 0 limit I want you to see, which is the following. Let's say we have the limit as x approaches 4 of, sure, 8 over x minus 2 over, yeah, sure, x minus 4. Once again, a 0 over 0 limit. The previous one, when we had square root to multiply by the conjugate. Here, what we're going to do is we're going to get a common denominator. So I'm going to re-express this as limit as x approaches 4 of 8 over x minus, I'm going to multiply the 2 by x over x to get a minus 2x over x, all over x minus 4. And then I would encourage you to rewrite this the following way. I'm going to rewrite 8 over x minus 2x over x as one fraction, right? Because that's why I got a common denominator, so I can subtract them together. So 8 minus 2x over x. And instead of dividing by x minus 4, we would like to multiply by what? Right, 1 over the thing. So then we can write this as just kind of one fraction instead of like a fraction and a fraction. In the numerator, I would like to factor out a -2. So I'm going to factor out a -2. I'm going to be left with a -4 plus x. And the denominator, I don't want to multiply with the denominator. So I'm looking to make that x minus 4 cancel. Multiplying it out doesn't help me see that it cancels. So I'm going to leave it as an x times x minus 4. Can I cancel anything? Are those the same? Yeah, they are. You can totally rewrite it. You can rewrite it as the limit as x approaches 4 of -2 times x minus 4 over x times x minus 4. But you don't need to if you don't want to. So those cancel. And left with the limit as x approaches 4 of -2 over x, which is -2 over 4, which is -1/2. So the mantra, for lack of a better phrase, for 0 over 0 limits is the following. For 0 over 0 limits, we usually like to say, do some algebra. Now, that's not 100% always effective, but it's often effective. And by algebra, specifically, we mean either factor and cancel, or first multiply by the conjugate, and then factor and cancel, or get a common denominator, and then factor and cancel. That's what we kind of mean by do some algebra. That's not to say that these are the only types of 0 over 0 limits. Now, I wish I had like another half hour. So, now, come on, maybe my fingers work better. What about this limit? The limit as x approaches 0 of sine of x over x. If you haven't gotten there yet, you will soon. Unless your teacher decides to skip it, which is probably not okay. So I'll show you. You know, we have a lot of time, but anyway. Here's what this function looks like. Looks like that. And if we zoom in maybe just a little bit, you can see that as the x values, well, look at pi, you get 0, great. as the x values get closer and closer and closer to 0, what are the y values getting close to? We're getting closer and closer to 1. But when we actually get to 0, I passed it. So I will say one thing, it's not actually equal to 1 there. It's just the decimal approximation is so close to 1 that that's what they're writing. Actually like 0.9999 something. But when you actually get to 0, can you actually get there? You can see it for a second, it's undefined. Oh, yeah, undefined, undefined, undefined. Okay, so when you plug in 0, it's undefined. You get a 0 over 0. The sign of 0 is 0, and x is obviously going to be 0 as well. But this limit is equal to 1. Now, there is a geometric proof of this. I think I did post it in Canvas. I'm not 100% positive now that I say it out loud. But let me actually, oops, try to do the thing over here. If we look at Canvas real quick. Yeah, let's leave. It's almost time to be done. Oh, come on, don't log in. Crazy. So if you want to, let's see if it's there. If it's not there, I'll make sure I put it there. I'm pretty sure I put it there. Modules. There's all the stuff. And that's, yeah, right there. Proof of the limit of sine x over x, x goes to 0 is equal to 1. So not that I'm not happy to talk about this if you want me to at some point. It's not that long. It is a geometric proof. It's kind of neat. It's also probably not super vital that you see it. If you want to see it, great. I love talking about it all day and all night. But as you can see, I'm always running out of time here. So it's probably not the best use of your time. I would encourage you to take to heart the graph that we just looked at. Can you get back there? Maybe not. Yeah, maybe. So I would encourage you to think of, oh yeah, when you're thinking of sine of x over x, think about this graph. It definitely gets closer and closer to 1 as x goes to 0. Now, the point here really is that in general, if you have the limit as some stuff goes to 0 of sine of some stuff over the same exact stuff, that's always going to be 1. So just a couple examples that we're not going to prove. Oh, sorry, you can't see the thing because I'm a dork. Oh, sorry, I keep doing that. So for example, the limit as x goes to 0 of sine of 6x plus x, that's done, that's 7x, over 6x plus x would equal 1. Because the stuff is the same and it's going to 0. Or the limit as x approaches 3 of sine of, I don't know, 2x minus 6 over 2x minus 6 would equal 1 because it's adhering to the same pattern. You've got sine of a thing over the exact same thing, and both of those things are going to 0. Yeah.
So it doesn't have to be to 0.
Right, it doesn't have to be to 0. So I know I've seen questions before, like where it's like the limit as x goes to say something like pi over 2 from the right of sine of x minus pi over 2 over pi over 2. And, or sorry, x minus pi over 2. And that limit's 1. As long as you meet the two conditions. The stuff in the sign and the stuff it's divided by are the same, and they're both approaching 0. Those are the two things that have to be true for this limit to equal 1. So just as a different example, the limit as x goes to infinity of sine of x over x is not 1. It's not meeting the criteria. Yeah, the stuff is the same, but the stuff is not going to 0. And we'll show next time, because we're out of time, that this limit's 0 by the squeeze theorem. But I should stop talking because it's 3:01.